One of the most difficult concepts that I came across to teach when I did my first year of teaching chemistry was atomic structure and getting kids to really understand what's happening during the flame tests. Conducting the flame test lab was one of the more easy things that I had done, but then trying to explain to my students what's happening and how we know that there are all of these orbitals and different energy levels and that electrons can move in between them was really one of the most difficult things to cover. It took me a long time, and I realized that I presented almost the entire lesson just doing lectures. A really great teacher retired before I got my current job, and she told me about something that she did right around Halloween time. And by that point in time, we've covered the basics of atomic structure. We haven't gotten to orbitals or electron configurations yet, but we have gotten into the structure of the nucleus, protons and neutrons and isotopes, ions, and we had just started getting into what electrons are doing. So on Halloween, the kids come in. All of the blinds in my classroom are pulled down. The room is completely blackened or capable of being blackened when I turn the lights off. And we spend the day in the dark. And I talk about the essence of chemistry. And when I say the essence of chemistry, I'm not quite talking about what they're talking about. We're talking about all of the other essences. We're talking about incandescence, fluorescence, phosphorescence, triboluminescence, chemiluminescence. All of the different ways that chemistry gives off light. And it's all a reaction to electrons being excited, dropping back to their ground state, and giving off light. So it really allowed me a really great, fantastic set of demonstrations. And my classes are 45 minutes long, and I spend 40 of those 45 minutes just doing a barrage of demonstrations that correspond to excited electrons. Given that it's around Halloween, things glowing in the dark, all of the glow sticks and all of the stuff that's going to happen for Halloween ties in at a really convenient time in the school year. There was a really great demonstration that I saw when I attended Chem Ed in 2003 of a teacher jumping up and down between different energy levels. It was the most marvelous explanation I had ever seen of explaining how electrons are exciting up and down and how different wavelengths of light can actually be given off in the process. It's a completely non-mathematical explanation other than counting. And it really solidified for me in my own mind, oh, that's a beautiful way of demonstrating this. So I'm going to demonstrate that for you now, and I use this demonstration at the beginning of my day in the dark to explain every single thing else that the kids are going to see that day. So what I start with, I have photons, and they're just colored spheres. These particular ones are street hockey balls. I got them in a sporting goods, actually might have even been a hardware store that I happened to find them that had them in their seasonal items. Any colored spheres will work. Walk down the toy aisle and find whatever soft thing you can get to throw out to the kids. And I just distribute them to my classroom and say that these are going to represent different wavelengths of light. And you can think of a photon as a little bundle of light. And we have different energies here. My kids often have a misconception because Crayola lies to them. They think red is the hot color and violet and blue are the cool end of the spectrum. And I have to reverse that and say, no, your art teachers in Crayola lie to you. It's the opposite way. The blue-violet end of the spectrum is really the high energy, and the red and orange is the cooler energy. So I'm just going to distribute these to a few of our audience members. Or I'll redistribute that one. There we go. And so now my students have various different colors of light that they can throw at me. And I've laid out in my class table, I use the lab table as the highest level. And then I have books or chairs or boxes or whatever I happen to find in my classroom that day to make the steps that go up. So what I explain is that each one of these steps is a different energy level inside of our electron. So we have a small energy level, we have a slightly bigger one, bigger and bigger. And electrons, when they receive energy, can go through an excitation and jump to a higher energy level. And the jump is complete. It's like rungs on a ladder. You can't hover in between rung number 2 and 3. It's just not possible. You either are rung number 3 or you're on rung number 2. That's it. You can't levitate somewhere in the middle. It'd be kind of cool if we could, but we can't. So what I explained to them is that if I'm going to jump, I'm on the ground right now, so I'm in the ground state configuration or the ground state position for an electron. If I add energy to an electron, my kids know energy is conserved. So if the electron absorbs energy, it's going to have to jump to a higher energy level. Now, my first energy level does not look very different between the ground and the first state. So I need a small energy photon who's got a small energy photon. Something that would correspond to low energy would be at what end of the spectrum? Yeah, the red end of the spectrum. So the person with the red photon hands me the electron, and I jump to the next energy level. My photon here, my red photon, not the electron, sorry, makes the electron go to a slightly higher energy level. So now I have a little bit more energy than I had before. But one of the interesting things about electrons is that, kind of like people, they go to the lowest energy state possible. So we can take this electron and give off the light, and this electron now drops back to the ground state as soon as the photon is emitted. So in the process of absorbing the photon, we can go up an energy level, and then dropping back down, we release that photon, usually in the form of light that we can see. This is how we got all of our atomic structure knowledge, was by looking at the light that's coming off of these things when they become excited. Now, I have another energy level here. I've got a second energy level. It looks like the difference from the ground to the second energy level is larger. So I need a bigger energy photon to get here. Who's got a bigger energy photon than red? All right, we have an orange photon, so I need an orange photon. And I can jump, once I absorb that photon, I can jump to a higher energy level. I'm in an even more excited state than I was previously. Now, I'm not going to hold on to this energy for all time. I'm going to drop back down to the ground state. Now, I have another energy level here as well. This energy level is even higher than my previous energy level. So I need a higher energy photon. And we have a higher energy photon than orange. No one does? Someone has yellow out there? Okay, so let's take yellow. Well, the photon didn't hit the electron that time, so let's try one more. There we go. All right, and well, nothing happened. If the energy of the yellow photon doesn't match the energy difference between the ground level and the next level, electrons don't jump. We can't hover halfway in between two rungs of a ladder. Electrons can't jump halfway in between the second and third energy levels. So if the electron's energy to the next energy level doesn't match the photon, no excitation happens. So this one didn't result in an excitation. Does anyone have a higher energy photon? Maybe we need more energy to get to our third level. All right, so we've got another one, green, and we're even more excited state now. We're getting into a higher energy level, and then when we give off that light, again we drop to the ground level. Now, I do this in my classroom. My lab tables are high enough, and I'm still of an age that I can actually clear this. If you can't do this, you by no means have to do what I'm about to do. You can easily go to the staircase in your class or in your school in the hallway and just climb up and down staircases. I had one lab table actually that was too high for me, and so I just did prop myself up and then go there. This one is fortunately the right height and is ballasted very nicely to the ground, so I can actually clear it. Does anyone actually have a higher energy one than that? Okay, so we've got blue. All right, and so now, whoops. Let's try it one more time. Now I've got a whole lot of energy. I'm in a really excited state. And then when I drop that energy off, I go back down to the ground state. So it's a really dramatic demonstration that makes it really easy for your kids to visualize what's actually happening inside of our atoms when these electrons are jumping through excited states. I use this excited state example to explain all the stuff they're about to see, which is the cool glow-in-the-dark stuff and the fluorescence. And we're going to break now, and I'm going to set the table back so we can look at some fluorescence and phosphorescence demonstrations. All right, we're back. We're going to look now at a couple of the essences of chemistry. When I first start this lesson, I give my kids a list of definitions. I actually write all the names on the board because they don't actually know how to spell any of them. But then the one that they are already familiar with is incandescence, the idea that a really hot object can glow, can emit light. So they're familiar with the incandescent light bulbs, like the tungsten filament that's in their light bulbs at home. That gets hot enough that it actually emits light. So that's the easy one that we get out of the way. Then I have to define fluorescence for them, and I don't quite give them a word definition at first. I do a series of demonstrations and start to explain using the excitation demo and the jumping teacher demo that you just saw to explain really what's going on inside of the atom that causes fluorescence to occur. Fluorescence is just a situation where an electron receives energy, it can come from a variety of forms, jumps to an excited level, and then will return back to the ground state to emit that light again. Now, once it jumps to that excited level, there's a variety of different things that can happen. It can go through intermediate states and then fall back down. So sometimes the light that we get from fluorescence is very different than the light that we excite with, or the light that you would normally see under visible light like we can normally see. So I use a series of demonstrations. I have a blacklight UV lamp here. You can use a regular blacklight like you find in various stores and party stores that have those glow-in-the-dark effects and those weird psychedelic shops. I find that this one's a lot better. This is one of the ones that's used by mineralogists. This has a shortwave and a long-wave ultraviolet irradiation. The important thing about this is you need to make sure that you and your students are wearing safety goggles, or that you are keeping this pointed away from your students at all times. Long-term exposure to ultraviolet light can cause cataracts and other eye damage, and that's not something that anyone wants. Honestly, I'm the most at risk here, so I make sure that I'm always wearing some kind of a safety goggle that has UV protection. My eyeglasses also have UV protection, the way that they're the film that's on them. Visor goggles also. Most safety glasses are actually UV protectant, and you can find other UV protectant goggles if you don't have visor goggles or a goggle that has them. But make sure that you have some kind of protection on your eye, because that is probably the biggest hazard in any of these demonstrations. I then show my students a variety of objects that will undergo fluorescence. I do explain to them what's happening, but I show them the objects first to give them an interesting idea or something fascinating to look at, which is way more interesting than hearing me explain, here's what's happening with fluorescence, and now let's look at something that's fluorescent. I find it's much better to hook them first, then get a little bit of teaching in, and then bring them back and hook them in again. So I'm constantly going back and forth when I do this day in the dark between the board and a new demonstration, a board and a new demonstration. But it's a good 45 minutes of really cool, amazing stuff with a little bit of chemistry knowledge to back up what's going on. But it really does add a lot of punch to my atomic structure lessons. So the first one I'm going to look at is just a variety of fluorescence. Even before I get to fluorescence, I do talk about excited electrons, and that sometimes we can actually trap excited electrons in their excited state. If you've ever seen the irradiated salt in nuclear reactors, they line the outside of the reactor with regular table salt. You can order irradiated salt. Flynn carries it. There are also a variety of places that also sell it. Flynn's, for me, the easiest place to get it. And you take a really, really hot plate, sprinkle the irradiated salt on it, and you can actually see the electrons emitting the photons as they drop back down to the ground state. So that's the first one that my students see. Then I go into fluorescence and talk about temporary excitation of electrons instead of a permanent excitation. So we're going to be going on and off through various lights, but I'm going to show you guys several fluorescent materials that I have. The first one that I'm going to show you guys, and if we can take the lights down a little bit. If you take Vaseline, you can see that under shortwave, you get quite a very large amount of fluorescence. And this kind of blows my kids' mind, because this is something they are familiar with and probably never even considered that it might be fluorescent. What my students consider fluorescent are highlighters. And there are other materials as well. If I take, in Michigan, our driver's licenses, and you can check yours as well, our driver's licenses are actually printed with some fluorescent dye so that under a black light you can see if they're a fake ID or if they're a true ID. If you have a $20 bill, and this might be difficult to see, I'm not sure if the camera will pick it up, there's a little strip inside of almost all of our bills now to prevent some of the counterfeiting. And there is a slight red-orange fluorescence that happens on the strip of the $20 bill. Can you guys see that at all? All right. There's several other ones as well. If we can bring the lights up just a little bit, I have to grab a few more objects. If you go to flea markets, or if you've ever seen anything of the Depression-era glass, it's got that sort of eerie green glow to it. And that's because they added uranium oxides to the glass. It gives it that really, really brilliant verdant green color. If you have any of this, or you go to a flea market and find it, it's very characteristic. So just pick up a piece. Find a piece that's chipped. This one is not really worth any money. There's a small chip on the handle, and so it's not worth that much. It's not in pristine condition. You don't care what it looks like. You just want the glass itself. So I just go ahead and find whatever I can whenever I'm going through a flea market or any sort of garage sale, or if you've got time during the summer. But this one shows a really dramatic fluorescence, if we can bring the lights down. When I turn the light on, it's really a fantastic eerie glow that happens. And it's because the uranium oxides inside that are trapped inside of the glass, now that we're irradiating with ultraviolet light, are emitting visible light as those excited electrons drop back down to the ground state. Now, one interesting thing to point out about fluorescence is that as soon as I turn the light off, the fluorescence is gone, and we can bring the regular house lights back up. Fluorescence is an almost instantaneous thing. The transition in time between when the electron jumps and falls back down can be like 10 to the negative 12th seconds on average. In femtoseconds and picoseconds, we're talking instantaneous up and down. We're not talking about long-term delay. We're going to get to that a little bit later on. So those are some fluorescent materials that I show my students. There are other ones that I show as well. I mentioned that when you go down aisles of the supermarket, and my students don't even realize that this happens. I think that they've been raised in a generation, and I was part of this generation a little bit too, that was so used to advertising that as soon as a commercial comes on television, you're just not paying attention anymore. So my students think that they're beyond advertising, that they're smart enough and they're not going to get caught up in advertising and, oh, I never listen to commercials and whatever. They don't even realize that advertising is happening without them even knowing that it's there. If you go down the laundry detergent aisle, everything is very bright. You have bright colors, bright neon, and well, not truly neon as we know, but very, very bright fluorescent colors. If you go down the canned food aisle, though, you don't get that same experience. Well, clothing manufacturers know, and detergent companies know, that you want your clothing to be bright and clean, and you associate vivid color with very clarity and cleanness. So they wrap their packaging with fluorescent dyed materials so it looks bright and vivid and clean to you. Food manufacturers don't care about this. Your food's not supposed to look clean and bright to you. It's supposed to look appetizing. And so they don't use a lot of neon and fluorescent dyes to try to lure you into the idea of buying their product. Now, my students don't always believe me even when I put them side by side. They're like, yeah, one of them's kind of bright and one of them's kind of not. But if we take the lights down and we look at these under ultraviolet light, a whole new picture starts to emerge. You can see that the canned food item looks really remarkably unaffected by our fluorescent light. But the Tide, any laundry detergent works really nicely for this, gives you a very bright, vivid fluorescence. So what happens when you put fluorescent dyes onto some kind of a substance and you're looking at it under regular light? Well, if you bring the lights up back for 1 second. When you look at these things under very bright light, or any white light reflects things back. Well, our eye can't see anything past violet. But if you have ultraviolet light that is bouncing off of something, exciting electrons up, and when that electron drops back down, it releases something like blue light or violet light back to your eye is getting more light than it was getting previously. So it looks brighter. More light is making its way back to your eye. Even though we can't see the ultraviolet, it looks brighter to us. Well, that's exactly what clothing manufacturers and detergent company manufacturers want us to see. Bright light coming from their product. And the interesting thing about Tide, or any detergent actually, most of them now have whitening stuff inside. And the advertising campaign, I remember this from my childhood. I think the new generation is a little beyond this now, but you can still bring it up. Tide gets whites whiter and gets brights brighter. Well, they're not adding dye in there to make white come out whiter, and they're not adding dye to make all of your colors come out brighter. What happens is they have fluorescent compounds in the actual Tide itself, the actual detergent itself. So the way that it gets whites whiter is because it's taking ultraviolet light and starting to reflect it back to your eye. So you see more light coming off of an object. So it appears brighter because more light makes it back to your eye. Our eyes only see what's reflected back into them. So if we look at the Tide detergent itself, and we can bring the lights down, it looks white under regular light. But under ultraviolet light, we can see a very, very clear fluorescence happening from all of the UV-sensitive compounds that they put inside of the detergent. That's how they make the whites whiter and the brights brighter. And if we can bring the lights up one more time. Thank you. Now, when I was in college, I commuted to school, so this didn't happen. But friends of mine who stayed in dormitories said they used to have blacklight parties, where they would, the kids would get one of the UV ballasts and put it up in the fluorescent lights, and they would paint the walls with Tide, which isn't really damaging the wall, but you could get very brilliant pictures illustrated. They'd also take highlighters and put them into the walls as well, and you could make all sorts of psychedelic patterns out of the fluorescent highlighters. The highlighters themselves are actually sort of an interesting thing. I have some fluorescent highlighters over here, and I'll bring them over. I just wrote with several different brands of highlighters in several different colors. Some highlighters are fluorescent, some of them aren't. They all look bright. They are all very vivid colors, vivid pastels in our eyes when we're looking under visible light. But the interesting thing is that if we put them under ultraviolet light and we bring the lights down, you can see that not every fluorescent marker is actually fluorescent. So you can see the pink marker, which was at the top, sort of gives us a yellowish green color. The yellow marker fluoresces as orange. Actually, that's the orange marker fluoresces as orange. The yellow marker and the green marker both fluoresce as green. And then the pink at the bottom is a bright orange color. But the blue that was in the middle, and let's bring the lights back up so we can see that a second time. The blue that's in the middle doesn't contain fluorescent dye at all. So not all highlighters are actually fluorescent. And I usually have the kids just give me whatever highlighters they had in their backpack that day, and I write something on a sheet of paper and show them that some of their fluorescent markers are fluorescent and some of them aren't. I also have fluorescent crayons, and any sort of thing you can find in a gimmicky shop that you can demonstrate fluorescence are really good things to bring in at this point. There's another really important one historically that we dealt with well before my time, when malaria was a much more real scare for people in the United States and our veterans that were fighting in wars than it is today. And that's the one that deals with tonic water. Tonic water contains quinine, which is a compound that was useful in the treatment and prevention of malaria. They actually added it into the tonic water because they were trying to find a way to get the soldiers to actually take the quinine. They were actually resisting taking it. And so they put it into their tonic so that when they had their drinks, they would get it without them even knowing that it was there. Well, now they have to say that quinine's there. But if we take the lights down, we can see that it's clear and colorless under regular light. But under ultraviolet light, your tonic water gives you a very sort of brilliant bluish color. And in the bottle, it's not that great. So I usually tell my students that I don't like the flavor of tonic water very much. If we can bring the lights up just to maybe about halfway. Thank you. I tell my students that I don't like the flavor of tonic water at all. So I'll usually take a sip of it and say, maybe my tastes have changed. I don't know. We'll give it a new try. And so I take a big healthy swig of it, and as soon as I take a swig, we're going to need to bring the lights down again. Yeah, still don't like the flavor. Let's bring the lights up one more time. I do find that there is importance in being eccentric in your classroom, and if you can get your kids to believe that you're as crazy as they really think you are, it really can become a phenomenal asset later in the year. But my kids really do enjoy seeing this one and watching me basically vomit up tonic water under fluorescent light. So fluorescent vomit is a really nice way to get your kids to have a nice gag at your expense. One important thing about using tonic water in pretty much any carbonated beverage in your classroom, go with the diet brand. I found this out the hard way once. Sugar gets really sticky when it dries on your floor, and so make sure that you go with the diet one, so if you miss the sink, it's a lot easier to clean up rather than washing your floors at 4 o'clock in the afternoon, or the janitor's coming in and you're sticking to your floor getting a fruit fly infestation the next day. But that is really a wonderful demonstration. I usually do it for my students twice because they get such a kick out of it the first time. You can also show that now with all of our whitening products in toothpastes and so forth, you can show that your teeth will fluoresce as well. Make sure that when you do this, you angle very carefully so you're not shining it into your eyes. You want to shine it from the top down. But I can show you mine now if you want to take the lights down one more time. You can see that lots of times teeth will also reflect a lot of ultraviolet light. And particularly if you swish with the tonic water beforehand, you can also demonstrate that. All right, bring lights up one more time. Thank you. So from this point, my students have some pretty good idea of what's happening with fluorescence, and they've seen a lot of really good fluorescent demonstrations. So I'm going to go to the chalkboard and show you a little bit more of the chemistry that's happening here. And I bring this up to my students so they can see really what's going on. In the ground state, we're going to have our little electron. Well, what happens if we blast that electron with some energy, either in the form of ultraviolet light or a photon or electricity or heat, sometimes even the energy released from a chemical reaction? All of these are ways that we can excite an electron. Well, when we add energy, that electron is going to jump to an excited state. And there are a variety of excited states that an electron could probably exist in. So once it gets to that excited state, there might be other excited states that it could gradually sort of work its way down through. It doesn't have to only be in one excited state. And these excited states are usually fairly close to each other in energy. So it could be the difference between, if you're talking orbitals 2s and 2p, or even 4s and 3d, which is a very small difference in energy. So there are a variety of vibrational, rotational, all sorts of different excited states that can be excited through. When these relaxations occur, it's not a big enough energy difference to make light that we can see. But when it drops from here back down, that wavelength of light that is given off is our fluorescence. That's what we see when we're seeing fluorescent materials. Well, this energy difference is not the same as that energy difference. So when that change in energy happens, it doesn't have to be the same color. In fact, is often a lower energy color than what we excited with. So when I excited with ultraviolet, you saw greens and blues and oranges. Those are all much lower in energy than ultraviolet light is. So it helps my kids to see that the reason we're seeing different colors is because it's actually dropping from a different energy standard. But we can figure out, if you want to go into the mathematics, in my intro chemistry class I never do this, but you can use E equals h nu to correlate the energy of that wave, or the wavelength of that wave, or the frequency of that wave, to the energy difference between the levels that are being jumped through. So if you want to tie this into an advanced chemistry class, it's another way of talking about the mathematics and going for a more quantitative approach and less qualitative. One of the interesting demonstrations that I saw at a chem ed a while ago dealt with sunscreen. And I, in my classroom, am always looking for real-world connections between what I teach my students and what I actually demonstrate to them. I think that you learn a lot more chemistry when you actually say, yeah, this does actually apply to something that I'm doing. I give my students a project at the end of every school year that deals with writing poetry about chemistry. And so it's called chemoetry, and they have to write a half page or 3/4 of a page of poems about anything that we studied over the course of the year. One of my students wrote one about why I hate chemistry. And she says, keep in mind, this is not, she was really worried about her grade, but the beauty of the poem was she kept saying how she hated chemistry because now she can't look at the world around her without seeing it everywhere. And that really is what I want all of my students to be able to do when they leave my class, is just see the world around them as a series of interactions with atoms. So the more places you can pull in everyday life, I think it's the more meaningful it becomes. So this demonstration deals with something that many of my students have seen, but they don't know that they've seen it. This is fluorescein dye. You've probably seen fluorescein dye in antifreeze before. Antifreeze is containing a compound that's fluorescent. My dad's a veterinarian. Very oftentimes dogs or cats, dogs especially, will lick up antifreeze if it drips when you're filling your reservoir in your garage, or if it's a leaky system inside of your automobile. The glycol, or the propylene glycol that they use now, tastes sweet. And so the dogs don't know. It doesn't, this tastes good, and they'll lick it up and get very, very severe problems as soon as they ingest it. They can actually look at the urine that comes out of the animal, put it under a black light, and see if it contains the propylene glycol, because the fluorescein will fluoresce. It passes through your body undigested, so they can see that on the other thing. So I usually bring that up to my students as a place where actually this fluorescence is used to save lives of animals. But other places, cat urine also fluoresces. If you want to collect it, go ahead. I never have. But the fluorescein is a really dramatic one, and what it can be used for is to determine what's happening when we use sunscreens. Now, for this demonstration, you want to get a sunscreen that's colorless, and, well, color is not as big of an issue, but make sure it's not one of the opaque ones, that's the creamy ones. You need a spray-on version. And all I did is I went through my pharmacy and looked inside and see if I could see through it or not, and if you can, then get that one and buy it. So this is just a 30 SPF, 15 works too. But what does a sunscreen do? It protects us from the harmful ultraviolet light that's coming from above. So when we're looking at ways of protecting ourselves, how can we show what a sunscreen actually does? Now, I want to show you fluorescein just as a fluorescent substance itself. So if you can bring the lights down. you can see that you get a very bright, vivid fluorescence from the fluorescein. So it's an incredibly fluorescent substance. This is shortwave and this is longwave. For whatever reason, play if you have a dual setting on your ultraviolet light that pick the one that gives you the brightest fluorescence for this demonstration. If we can bring the lights up one more time. So my students have seen what this looks like under the ultraviolet light. So what I do is I take a Petri dish. This is just a Petri dish cover. This is the polystyrene disposable ones. And I just spray them with the sunscreen. Get a nice healthy coating, but not too much, obviously, because you don't want to think that it's because you had this thick layer of sunscreen, all of a sudden light's not going to get through. But they can see it's clear, so light can get through. It's transparent. And then because it's such a low mass, it'll actually just stick on the bottom of your beaker. And if we can bring the lights down one more time. You can see when we illuminate from the top, oops, one more time, there we go. When we illuminate from the top, it's very bright. We get quite a vivid fluorescence. But if I switch it to underneath, there's really a dramatic change in the fluorescence. You don't see nearly as much light being fluoresced. Well, why would less light be fluoresced? And then the other issue that my students have is, oh, well, it's because it's the Petri dish and whatever. So what I often do at this point is I'll leave the ultraviolet light set up, and I will grab another beaker from underneath here and actually pour out some of the solution that's on the top. So they can see that it's coming from the same jar, but if I pour it into a regular beaker, there's a huge difference in the fluorescence that's experienced between the two sides. So it's a really dramatic illustration of what is a sunscreen doing. Well, let's bring the lights up and let's talk about this for a second. So what does a sunscreen do? A sunscreen takes ultraviolet light, absorbs it. The compounds in the sunscreen itself absorb the ultraviolet light, goes through that intermediate energy transition, and then releases the light as lower energy light, light that's not harmful for our skin. So maybe blue or green light or something like that. It just takes the energy of the high energy, converts it into a lower energy form of radiation. That's why we want to protect ourselves. Now, I did switch to using the plastic ones here. I had a student teacher this year who had a major in biology and minor in chemistry. He informed me because his biology research was in culturing Petri dishes. They used to use the polystyrene Petri dishes to prevent ultraviolet light from getting into it. And I looked at it and I said, oh, even without the sunscreen, the Petri dish conveniently blocks out a lot of light. So if you want to be more authentic, I don't tell my students this because they're not at a level to understand the difference, and it gives me the same effect and it's a lot easier of a cleanup. If you want to see what it looks like with the glass, you can do it with a glass Petri dish as well. So if I just pour this into the glass beaker and spray the glass Petri dish, and if we can bring the lights down one more time. So here's under, oops, there we go. Here's under regular light. And then this is the test of my dexterity, because this is why I stopped using the glass dish, as it was hard to handle. And we'll invert it upside down. You can still see there's a really dramatic quenching of the fluorescence when we are dealing with light going through the sunscreen versus light not going through the sunscreen. So a really handy way to tie this into everyday life is to look at what's happening with everyday products. Can we bring the lights up one more time? Thank you. So those are all the fluorescence demos that I give my students. One of the things that you can also test out if you have the ultraviolet sensitive beads, Flynn Scientific sells these, a variety of people do. These will change color when exposed to ultraviolet light. So we'll do this on just on the tabletop here. And if we can get a close-up there. You don't even have to do this under, these aren't going to fluoresce nearly as much, but if you have them under ultraviolet light, you can see that they start to change color. So it goes from colorless to variety of different colors. There's a teacher in Michigan who gives this to their students as a first day activity. They give them a couple of beads on a pipe cleaner, and they tell them to tie it around their wrist and just make observations for 24 hours. And what they notice is when they go outside, suddenly it's a different color than when they were inside. And so then after that, they come in and they do an inquiry experiment the next day where she just lets them design an experiment of what can we do with this. So some of them pull out sunscreen and see what happens and so forth. But it's also a handy way to show what ultraviolet light can also do. So from here I move from phosphorescence into fluorescence. from fluorescence into phosphorescence. The only difference between phosphorescence and fluorescence is usually a delay in time. Phosphorescence takes a long time, and my students don't know the term phosphorescence all the time, but they do know the term glow in the dark. And what glow in the dark is, I tell them, is phosphorescence. And I usually give them a little parenthetical. Glow in the dark is the same thing as phosphorescence. It's called phosphorescence because phosphorus or phosphorus compounds were responsible for most of the glow in the dark activity. Phosphorus is not required anymore, but we have a variety of compounds that don't use phosphorus, but that's where the first one started to happen. So there are a lot of variety of glow-in-the-dark materials that you can probably find. And you don't have to do these under ultraviolet lights. There are a lot of products of like stars that you can stick to your ceiling for children's rooms. And you can show the ultraviolet light, the effects of ultraviolet light on this. So I'll just illuminate this for a little while. You can do this under visible light too. This does not require ultraviolet light. You just get a little bit of a brighter glow from ultraviolet light than you get from regular light. And if we can bring the lights down and get a close-up of this. So students are fairly familiar with this. They've seen this before, a glow in the dark, that if you add more light to it, you energize more electrons and you get a brighter glow. And if we can bring the lights up one more time. So this one they've seen before, but there's another version. You can get a sheet of this phosphorescent material. Make sure that you keep this inside of dark cardboard or something so that it doesn't get illuminated accidentally, because then your entire demonstration is ruined. But if we bring the lights down, let me get this out first. All right, can we bring the lights down? Thank you. And you just put some kind of an object over this and put the ultraviolet light on the top of it. And when I pull that away, you can see a very clear fluorescence or phosphorescence happening here, a delayed fluorescence essentially. So these excited electrons are dropping from a higher energy level to a lower energy level. That's why we're seeing light, but it's doing so at a slightly different rate. And if we can bring the lights up one more time. And there's another demonstration you can do. If you get LED lights from a hardware store, Flynn I think sells a few of them as well. These LED lights can be used to demonstrate a similar concept about the energy of light. They now sell LEDs in all sorts of different colors. Usually you can only get them in red, I think was the first color of an LED that they came across. Now they have them in blue and green and then white, which is really just a combination of a couple of other LEDs. But they come on little keychains, so they look something like this. And so you can get different colors of LEDs as well. So that's one color, and let me pull out, I think red might be the other one. Sorry, trying to keep from illuminating this. So we've got blue and, appears to be blue and yellow are the two colors. And if we can bring the lights one more time, I'll pull out another phosphorescent sheet. If you can drop the lights one more time. Thank you. And this other phosphorescent sheet, if I illuminate it with the yellow light, and I'll hold this down so you can get a better shot. If I illuminate it with the yellow light, nothing really happens. It just looks like yellow light tracing around on a sheet of paper. But if I take the blue LED, you can get a very clear phosphorescence here. Well, why does that happen? The blue light is higher in energy than yellow light is. So you can trace fairly clear patterns because the blue light has enough energy to excite electrons up to the higher energy level, and then the phosphorescence takes over from there. If you can bring the lights up one more time. Another way you could demonstrate the difference in energy levels between red light and blue light or violet light under the spectrum. Flynn does sell a kit called Energy in Photons. And it is very important that when you use this kit that you keep the cardboard insert. But what it is here is you have different colors of light emission gels that, when exposed to different colors, will change the lights differently. If you have a theater department in your school, I just went down to the theater teacher and asked them for a series of gels, and they call them gels for stage lighting so they can make the stage look blue or green or yellow or red whenever they want to. Just go and ask them. A lot of times they'll have a little color wheel full of gels that they can give you. They get them for free from the companies. They look something like this. Roscolux is one company. And you can get the gels there too if you want to just demonstrate different colors of gels passing through light. But anyone who's worked in television or theater production knows exactly what these things are. But the interesting thing about this, and I'm going to hold this up against a white light or white background so you guys can see it a little bit. The gels are all different colors of the spectrum. So we have red, orange, yellow, green, blue, and violet in order. By the way, there is no indigo on our spectrums, despite the fact that everyone says Roy G. Biv. Isaac Newton added indigo. He was a rather spiritual person that believed in numerology and the significance of numbers. So he thought that 7 being a significant number, that the spectrum being a perfect thing should have 7 colors as well. So he added indigo in. Although Roy G. Biv is not nearly as mnemonic as Roy G. Biv, but there's not actually 7 colors. He just added 1 in. But the interesting thing about this is you can irradiate this either with ultraviolet light or actually, honestly, bright visible light works just as well. So if you have bright overhead lights, which we have here in the studio, thankfully, if you have a light box or an overhead projector, I usually, in my classroom, just flip this upside down on the overhead projector. That's a bright enough light that it's going to cause the irradiation to happen here. So with this very, very bright light from the studio, if we bring the lights down, I'll have this over here so we can get a close-up of it. When I bring the lights down, when I flip this up, you can see that there's only a couple of dots that have illuminated. Well, let's bring the lights back up so we can see what's actually happening here. Those are the ones that correspond to the violet and blue end of our spectrums. Well, it's a really nice way for my students to see blue and violet are higher energy than red, orange, or yellow. So it really reverses that notion that they have in their head from art class and Crayola that blue and purple are cool and red, orange, and yellow are hot colors. It really gets them to the right idea that blue and violet is the high energy end of our spectrum. So this was a handy kit that I found for getting that concept across to my students as well. I'm going to do the board so we can talk a little bit about the difference between fluorescence and phosphorescence. This same thing is going to happen in phosphorescence as it happens in fluorescence. That excitation is the same. The relaxation can even be the same. But the difference between fluorescence and phosphorescence happens to do with the way that the electrons are arranged in the highest orbital of the atom itself or the molecule itself. I don't go into this much detail with my students, but I think it's useful for me as a teacher to know this because you always might get that one student that asks you, but why? And so you can go into a little bit of detail to satiate that student, but it really is far beyond the level of an intro chemistry course. I even find it beyond the level of an advanced chemistry course. I do teach molecular orbital theory in my advanced chemistry course. If you don't even know what I'm saying when I say molecular orbital theory, don't worry about it. I'm going to try to explain it in a way that doesn't require that knowledge. But it really is a second or third year college level BS chemistry, physical chemistry course concept. So what happens here? The excitation is still there. There's a transition state that can happen in phosphorescence, though. So you have that primary excitation. So we're going to go from that ground state up to the excited state. And it can go through those energy transitions, possibly. It doesn't have to. But there's going to be some other transition into another lower energy state that those electrons can drop over to. Now, in order to do this, though, an electron has to go from one spin position to the opposite spin position. The spins actually change. That takes a lot of time. That is not a really quick natural progression of something to do. Electrons don't reverse their spins just automatically. So it's a really slow process. So this is a quite slow step in compare with fluorescence. Fluorescence happens on 10 to the negative 12th seconds. This can take several seconds, sometimes even minutes or hours to happen. So because this slow step happens, no light's released here. There's not a big enough energy difference. And then we can go through some other small transitions. But then it's going to drop back down to the ground state. Well, this is where we get that illumination of light. It takes a really long time, though, so some of them will do it fairly quickly. So you do see light right away, but you still see multiple photons being emitted over a period of minutes or sometimes even hours, depending on the material and the source of the illumination. So phosphorescence, I give it to my intro chemistry students as fluorescence that takes a really long time. because there's this transition that has to happen that takes more time. I don't really go into much more detail than that, and honestly, they're happy with that definition because they don't know that there's a lot more to the story than what they know, and at this point I haven't covered enough chemistry to really go into this kind of detail with them. But I do let them know there's a slight transition step here. I don't talk about spins because we haven't even gotten to spins yet. I do let them know that it just takes longer because there's an intermediate step that happens, and that's why it keeps glowing for a long period of time. So those are the demonstrations that I use to demonstrate fluorescence and phosphorescence in my classroom. I do go on one step from here. I go into chemiluminescence, and I let the students know that chemical reactions can also cause light to be emitted. So I will go through the instant light crystals. I'll take the big 2 funnels of the chemiluminescent mix of one solution and another with copper sulfate and luminol, and as it swirls, they mix together and you see a bright glow. I'll take light sticks and crack them and then put one in warm water, like 70 degrees Celsius. Don't get too hot, otherwise you melt the plastic, and that's not the desired effect. And you can put one in ice water and show the difference in the rates at which the electrons are emitted, or the photons are emitted. The rate at which the electrons are excited is a little bit slower, and the emission is a little bit slower, so you see a difference in color. So I follow it up with chemiluminescence, and then that ends the day in the dark. And by that point, we've gone through about 45 minutes of chemistry. My kids run out thinking I'm the best teacher on the face of the planet, and this is the coolest thing they've ever seen in their whole life. And then they go to history, and I feel good. So hopefully you'll find this as a way to add a lot of punch to your atomic structure lesson, a way to put some real-world context into what's happening inside of the atom, and help your students start to visualize what's happening with these electrons inside of energy levels, rather than just talking about things as, oh, we have light and flame tests, but here's a way to get a little bit more inside in a fun, non-threatening, and really exciting real-world method. Thank you.